Good afternoon, students. We have once again met for a new topic of physics called the electromagnetism. So what I have thought today, let's not discuss much into detail of the theory portion, because whatever feedback that we are getting from the live class from you, that you are asking for discussion on problems. So yeah, we'll be discussing few basic pertinent questions of electromagnetism, pertinent concepts. Then we'll see how we are solving problems on that. Okay. Now basically electromagnetism, what are the things that you have studied? If you remember, first concept is what is the force that a charged particle experiences when it is moving in a magnetic field. So means suppose this is a region of magnetic field. By the cross you can understand the magnetic field is in the downward direction, right? And a charged particle is moving like this, a positive charged particle, which is the direction of the charged particle is on the plane of the paper. That is, it is perpendicular to the direction of the magnetic field. So you will see the force that this charged particle experiences is nothing but, say the magnetic field is B, and the velocity with which the charged particle is moving is V, then is nothing but the product of Q into V into B. That is, we can write QVB. Now that is there's a multiplication of Q, V and B. Now this formula we have achieved because the velocity of the charged particle and the direction of the magnetic field, they are perpendicular to one another. But if the velocity and the magnetic field, they are at an angle of theta, then this force will be nothing but Q V cross B. Now V cross B you can understand is nothing but the cross product, which can be expanded into QVB sine theta. Now you can check when V and B, in this V and B, they are at 90 degree, that is theta equals to 90 degree, then sine theta equals to 1, the formula becomes QVB. When theta, if it is 0 degree, that is the direction of the magnetic field and the direction of the charged particle. Say direction of the magnetic field is this and the charged particle is either parallel or anti-parallel, that is theta equal to 0 or 180, then what will happen? The force will become 0, right? And now see, V is a vector, B is a vector, and the cross product, by the knowledge of cross product you also know the force, it is also a vector, that the force that it is the force, and what is the direction of the force, that we can get from the Fleming's left hand rule, right? In the Fleming's left hand rule you must be knowing that the forefinger, by this we denote the magnetic field, the middle finger, it denotes the direction of the charged particle, right? If it is positive charged particle, so this is the direction. If it is negative charged particle and moving in this direction, we take the direction in the opposite side. And the third direction is the direction of the force. So you can see that a charged particle which has moved into a magnetic field, say at an angle of 90 degree, it will experience a force which is 90 degree to both the magnetic field as well as its velocity. Now see what will happen if the force is in perpendicular direction of its velocity, then what kind of motion finally it will generate? You must be knowing that this is the velocity and this is the force. So for this force will act as a centripetal direction towards the center, and it will result in a circular motion of the charged particle, where this force is actually giving the centripetal force, which is nothing but mv squared by r, where r is the radius of the circular motion. Got it? This concept has a lot of application. Let us see. That is that we are talking about that when a charged particle is moving within a magnetic field, it is moving around a circle, right, where this force, which is nothing but mv squared by r, is given by the Lorentz force, that is BQV. In this case, only thing we need to remember to simplify, we have taken the theta to be 90 degree. Theta is between B and V. Now, if mv squared by r equals to BQV, VV cancels out, r, the radius which this charged particle makes, will be nothing but r will be mv by bq. Now r equals to mv by bq. What does this mean? Say mv is nothing but the momentum, right? So the radius which this charge the radius of the circular path in which the charged particle is moving is proportional to the momentum of the charged particle and inversely proportional to the charge of the charged particle, and definitely it is inversely proportional to the magnetic field. Now see, if this is the radius, we can find out what is the time period. Time t, if we say time period of one complete motion. Time period means what? Time to complete one rotation, isn't it? Right, that is what? This path is 2 pi r circumference divided by v, right? So it will be nothing but 2 pi mv by bq divided by v. So it will be what? Vv cancels out, 2 pi m by bq. The time period depends upon the, see, if magnetic field is constant, so we can take this part is constant. Time period depends on the mass by charge ratio of the charged particle. Got it? Whereas frequency is 1 by t, that you can find out is nothing but bq by 2 pi m. Okay. Now, with the momentum concept, you can also derive certain other formula from this. R equals to mv by bq. Mv is nothing but the momentum. Now momentum, if you relate it with kinetic energy, that can be written as 2 km by bq, where k is nothing but the kinetic energy. So that you know, right? That is P equals to root 2 km, right? We will keep all this formula in mind while we are solving problems on this, and we get really good interesting questions in joint entrance main. Let us see what kind of problems we get from this. See, one very interesting problem. Two particles A and B of masses MA and MB respectively and having the same charge are moving in a plane. Having the same charge. A uniform magnetic field exists perpendicular to this plane. Now see, in this case, the magnetic field is in which direction? Is in the upward direction, right? The speeds of the particle are VA and VB respectively. So they have different masses and they have different velocity. And the trajectories are as shown, right? Then you have to predict which will be the answer, right? Now see, in the trajectories you can understand the radius of R, that is radius of A, is greater than radius of B, right? Now what can be the answer? First see, they have compared the momentum. There also they have compared the momentum, and in this exactly they have compared each masses and velocity. Let us see. Now as radius of RA is greater than radius of RB, if you remember what is the formula of the radius we have just derived, radius is nothing but mv by bq. So instead of RA we can write MAVA by BQ, right? RB we can write MB VB by BQ. Observe, B and Q we haven't given any subscript. Why? Because it is said it is uniform magnetic field, so B should be equal in both the case, and also the same charge, means Q also equal in both the case. So this portion cancels out, which leaves MA VA will be greater than MB VB. That is, the momentum of particle A is greater than momentum of particle B. So the answer will be this. Okay, let's come to the second problem. This is also a very interesting problem. A proton, a deuteron, and an alpha particle having the same kinetic energy are moving in circular trajectories in a constant magnetic field. Again, what they have given? B equal to 0. Now first you have to remember what are the charge and mass ratios of proton, deuteron, and alpha particle. Now proton is nothing but, what is the mass? Mass and charge. Mass is 1, charge is 1, right? I'm not denoting the exact unit. You are understanding what I'm trying to say. For a deuteron, deuteron is nothing but 1 proton plus 1 neutron. So charge will be 1, mass will be 2 for deuteron. And for alpha particle, which is a doubly charged helium ion, charge is 2, mass is 4. Right. So we need to understand that is the ratio of the masses and the charges in these three particles. Now B, sorry, I have written 0. It's not 0 but constant. Right. Having the same kinetic energy are moving in circular trajectories in a constant magnetic field. Okay. Then we can write like R we know what? MV by BQ. MV is the MV is the momentum, but here they have given the quantity in same kinetic energy. So we can write it is root 2 km by BQ. Now see, R constant kinetic energy means what? K is constant, this part is constant, here B is also constant, so this part is constant. So R is proportional to root M by Q, isn't it? So we can say R is proportional to root M by Q. Now then what will happen? Say RA is to RB is to RC. If we say, it is definitely RA. Now R alpha, RP are deuteron. Okay, let us say like this. If R alpha is to RP is to RD, R alpha, for alpha root M by Q, alpha, it is definitely, this will be proportional to root 4 by 2, isn't it? Q, is 2. What is proton? For proton it is 1 root 1 by 1 RD. RD is what? Got it? Now root 4 is 2. This is 2. So this is proportional. This will be 1 is to 1 is to root 2. So what we can say, that is RD, the radius of Deuteron is the maximum, and which is greater than radius of Deuteron C. This is the answer. So R alpha is equals to RP, because both the ratio is 1 is to 1, and Deuteron is root 2. So this is the answer. Right? R alpha, RP, RD. Okay. Is it now visible? I'm explaining this once more. See, here 3 particles are given. What we are doing, we are first trying to tabulate the mass and charge of these 3 particles. Right? B is constant. So now, and they have given kinetic energy is constant. So we first brought the formula into kinetic energy formula. Now this part is constant. So the radius is proportional to root m by q. Now if you put it, it will be very easy to answer, which will be the answer. Okay. Now let us go to a different topic. So this was the charge moving in a magnetic field. Now what is a magnetic force on a current carrying conductor? A current carrying conductor, you know, that is nothing but, that is flow of constant charges. So this force you also know is nothing but I L cross B. Right? There it was what? B Q V, Q V cross B. Here also I L cross B. Right? Now here also the force you can find out with the help of either the Fleming's left hand rule. Also you can find out like this. If this is the current, right, we can use the corkscrew rule. That is, if this is the current, then the way we will think that the current is moving at the if we place the current carrying conductor in the along the thumb, then the way our fingers are curling, right, this way is the direction of the magnet. This is the magnetic force. Okay. Now see, this force, we are also solving a problem from this, right? Remember that magnetic field, right, force generated in the magnetic field is a conservative force system. So it depends only on the end path. So if a current is moving like this, right, in these 2 points A and B, right, along 3 paths 1, 2 and 3, this is the current, then what will happen, that is the force generated in this 3 path will be the same, though the length is varying, but the way it is being, you know, it can be shown that because force is a conservative field in this this force, so and they depend only on the 2 end path. Okay, we'll use this concept to solve a problem. Okay. In the figure shown, a semicircular wire loop is placed in a uniform magnetic field, B equal to 1 Tesla. Here given this B equal to 1 Tesla. The plane of the loop is perpendicular to the magnetic field, this loop, right? Current I equal to 2 ampere flows in the loop in the directions shown. Observe, in this, current is flowing like this. In this path A, C, D, current is flowing like this. In A and D, current is flowing in the same direction. So here the current is flowing like this. Whereas in this current is flowing this and it is returning back, right? Find the magnitude of the magnitude of the force in both the cases A and B. The radius of the loop is 1 meter. So this radius they have given 1 meter. Now, very interestingly, in number B, the current is moving in a loop. As it is moving in a loop, so finally the effective length of the conductor we will take is 0, because the starting and the ending point is same. So here the force generated will be 0. But in this, see, there are two paths, AD and ACD. But as it is a conservative force system, always remember, in a conservative force system, the force depends only on the end points, not on the path, right? And as it is a conservative force system, so what will happen? FAD will be equals to FACD, right? So definitely, and as the current is moving in the same direction, then the force generated will be also in the same direction, right? So the force generated, net force, will be equals to, we can say this plus this, which is nothing but 2 FAD. Now how will we find FAD? FAD is nothing but, if you remember the previous formula, the force is what? F equals to I L cross B. I L cross B. Now L and B, they are perpendicular to each other, is nothing but ILB. In order to remember very easily, we say it is BIL, right? BIL. Now it is 2 BIL. B is B is 1 Tesla. Current is 2 ampere, and length, this is the length. Radius is the radius is 1 meter, so that this is the diameter. This is nothing but 2 meter. So it's finally 8 Newton is the answer, right? So in any problem like this, where we are trying to find out the magnetic force on a current carrying conductor, we don't get confused with these loops. Just see where is a straight line path, because finally the calculation will be according to the straight line path, not on the curve, because finally the force will be same if the endpoints is the same, right? Okay, now I'm coming to another important topic. This we have done the force generated or experienced by a charge carrying conductor and a conductor carrying current, right? Now what move, like when a current is producing magnetic field, that we get by Biot-Savart's law. If you remember, suppose we take any conductor, right? Small dl is the length of the conductor, right? At a particular point, which is at a distance of r, we are finding the current. So finding the magnetic field, right? Small magnetic field dB will be equals to mu0 by 4 pi. Current flowing is I. By r square, that you know, right? Where mu0 by 4 pi, the value is 10 to the power minus 7 Tesla meter by ampere. Okay, mu0 by 4 pi, this is the value. B is measured in Tesla, obviously, right? Now, using the Biot-Savart's law, we can find out, we can get formula for many uniformly distributed current, such as first one, if there is a magnetic field around a straight conductor, current carrying conductor, you will see for this I was telling, like, if this is the current, if we put our thumb like this, the magnetic field will be around it, like in a circular fashion, right? At a point D, what will be the magnetic field B? B is nothing but mu 0 I by 2 pi d, right? Mu 0 I by 2 pi d. Now, what will be the magnetic field generated in a circular coil carrying the current? That is, at the center, B is mu 0 I by 2r, where r is nothing but the radius. Now, if this circular coil has a number of turns, if n number of turns, so B will be mu 0 ni by 2r. Now, what will happen for a solenoid? For solenoid, it can be found that B through the center is nothing but mu 0 ni. Now see, this is small n. Small n is nothing but mu 0 n by li, where capital N is the total number of turns, L is the length of solenoid, and therefore small n is nothing but number of turns per unit length. Okay. Now this formula we should just apply, right? We don't have to go into the details of the formula. There is another important formula, that is force between two current carrying conductors. Force between two current carrying conductors. So there are two conductors carrying a current, say I1, I2. They are at a distance of, say, R. What will be the force generated for these two conductors? I mean, with what force one will attract or repel one another? Let us try to see. First let us try to find out what is the B generated. Say I1 is our first conductor. At a distance of R, it is generating a magnetic field B. This B will be nothing but mu 0 by 2 pi I1 by R. Mu 0 by 2 pi I1 by R. Isn't it clear? Now see, this is the B, magnetic field generated at this point. Now, for a length L of the second conductor, the force is nothing but BIL. That is B, here I is I2 into L. That is B is mu 0 by 2 pi I1 R I2 into L. Now if you divide by L, we can get force per unit length of conductor. Unit length of conductor, that is mu 0 I1 I2 by 2 pi R. Right? And this is a very important formula. Even from this formula, we can find out we can define ampere also. Like mu 0 by 2 pi, mu 0 by 4 pi is 10 to the power minus 7, so mu 0 by 2 pi 2 into 10 to the power minus 7. Now this is force per unit length, r is the distance between the coil. So we can say, right, that is if 1 ampere current flows in both, right, so force per unit length and 1 meter is the distance between them. So force per unit length is nothing but 2 into 10 to the power minus 7 Newton, because this is 1 into 1, this is 1 into 1, and this is 1. So if two coils are there, if two wires are there, right, which are carrying 1 ampere each, they both are in the same direction. The distance between the wires is 1 meter. Force generated is this. Clear? Force per unit length of this conductor. Another thing need to be remembered. What is this force? Whether it is attractive or repulsive. Let us try to see it by the use of Fleming's left hand rule. See, as this current is in this direction, right, the B that is produced will be going downwards. Now what is the force generated here? Here the current is going in the upward direction and B is downward, means B is downward. I have put my finger like this, current, this middle finger in this, so see force is in this direction, means forces towards this, means they are attractive. And you can have another thought experiment. If the directions are opposite, then what will happen? Then also say this is I1, this is I2. For I1 the B is generated in the downward direction, right? Clear? B in the downward direction. Here current is in the C. B I have kept in the downward direction. Current is in the opposite direction. Force is outwards, means if force is outwards, means that is repulsive. So what we can deduce, when the two wires are carrying the current in the same direction, they get an attractive force. When the wires are in the opposite direction, they get a repulsive force. We'll try to solve a problem with this. Okay. Consider 3 long straight parallel wires as shown. Find the force experienced by a 25 centimeter length of wire C. Say this is A, this is B, this is C. Okay, now see A, C and B. A and C, they are in opposite direction. C and B, they are also in opposite direction. So what will be the force? What will be the force in this? It will be repulsive. It will be repulsive also. But see here the distance is less, so definitely the force will be more. Here distance is more, the force will be less. Let us try to first see F AC. Length is given 25 centimeter. Is nothing but mu 0 by 2 pi I1 I2 mu 0 by 2 pi I1 I2 R by L, right? Now mu 0 by 2 pi is what? This is 2 into 10 to the power minus 7. I1 I2 is 30 into 10 divided by L. R is 3 centimeter, L is 25 centimeter. So this is 3, this is 25. See, R and L both are in the same unit, so they will cancel out, right? So it has become, this cancels out, this is 10. So this is 50 into this 10 100, 10 to the power minus 5, that is 5 into 10 to the power minus 4 Newton FAC. And repulsive. Repulsive means for C, A will be pushing it in the right. Now what FBC? BC also, by similar calculation, we can see 2 into 10 to the power minus 7 into 10 into 20 divided by 5. 5 is the R, and L is again 25. Now 5 cancels out. 5 25, this is 5, right? This is 5. Now this will be how much? This 2 into 20, 40. 40 into 5 is 200. 202,000 into 10 to the power minus 7, that is 2 into 10 to the power minus 4 Newton. Now this is also force, but this is also repulsive, so as it will be pushing it in the left direction, in the left. So what is the net force on C? Is definitely this minus this, that is 3 into 10 to the power minus 4 Newton towards right. Got it? Understood this kind of problems? Okay. Now this kind of problems are more or less problems on electromagnetism, that is magnetic field and current. Let us do last one more problem, no more time, on magnetism purely. Very interesting topic, you know, angle of dip, angle of declination, and horizontal component of Earth's magnetic field. As a revision, if this is the Earth's magnetic field, right, and what is angle of dip? Angle of dip is nothing but the angle with which the magnetic needle is making with the horizontal, right? And what is angle? This is angle of dip. And angle of declination. Angle of declination is, you know, there are two meridians, right? One is a geographical meridian, one is the magnetic meridian. The angle between the geographical and the magnetic meridian is called the angle of declination, right? Angle of declination. Okay, you know, and what is the horizontal component of Earth's magnetic field? If BH is the horizontal component of the Earth's magnetic field, BV is the vertical component, and theta is the angle of dip, and BE is the actual Earth's magnetic field. So definitely BH, we can say BE cos theta, and BV equals to BE sin theta, and tan of theta is nothing but BV by BH. So if we know BH as well as angle of this angle theta, angle of dip, we can find out the other things. This is a very typical problem which usually comes, right? A magnetic needle suspended in a vertical plane at 30 degrees from the magnetic meridian. So the angle of declination they have given is 30 degrees because the magnetic needle is at an angle of 30 degrees with the magnetic meridian, right? So if this is the magnetic meridian, magnetic needle is in this direction, right? Which makes an angle of 45 degrees with the horizontal. Now 45 degrees is the apparent angle of dip. Now see, if suppose the horizontal Earth's component we will measure in the magnetic meridian, say if this is BH and this angle is 30 degrees, right? Then what is this one? This BH dash is nothing but BH cos of 30, the component of the horizontal magnetic field, in the magnetic meridian in a separate direction, that is we are at an angle of 30 degree, right? So BH dash equal to BH cos of 30. Now see, from this the magnetic needle is at an angle of 45 degree. Now see, BV is always same. BV is a vertical, right? So we can say 45 degree is the apparent angle of dip. So we can say it is angle of dip is measured in theta. So 45 degrees theta dash. So we can say tan of theta dash is nothing but BH dash by BV, right? Now tan of theta dash, BH dash is nothing but BH cos of 30, BH cos of 30 by BV, right? BH dash equals to BH cos of 30. Now see, BH by BV is actually tan of theta. Tan of theta cos of 30. This is tan of theta dash. So tan of theta, we have to find out the true angle of dip. So tan of theta equals to tan of theta dash divided by cos of 30. Understand? Clear? There is a mistake I have done. There's a mistake I have done. This formula I have done a mistake. Tan of theta is not BH dash BV. Tan of theta, sorry. Tan of theta dash is the angle of dip. Dip is vertical by horizontal. So tan of theta dash will be BV by BH dash. Now BH dash means what? BH cos of 30, that is tan of theta dash. Now BV by BH is nothing but tan of theta divided by cos of 30, that is tan 45 degree. So tan theta will be equals to tan 45 cos 30. From this we can find out the theta. This is also a very important kind of problem, right? I don't think we have more time today. I hope you have understood the points that we have tried to discuss. So practice problems and we'll see you soon. Thank you. No more questions?